Welcome to the Math Club today. It is my pleasure to introduce you. I'm Badawi of American University of Sharjah. Ayman and I have known each other since 1988. We've known each other for 35 years now. So he's a very good friend. He's very good mathematician, and he's going to tell us about numbers. And I can't wait for this. Ayman.
Thank you, Jim. Okay, I will be using only, there is nothing here, Alec, Martin.
That's just somebody that's watching you.
Oh, okay, all right. I will be, it's been a while, maybe at my university we use markers. And I think you do too.
And a lot of around.
Yeah.
We're old school.
So, it's been a while since I used that, so that's a pleasure, Okay. This is informal talk, entertaining. I always like to give talks, not, you don't have to be specialized or, just for fun, I call it. Okay, I remember Grant in his talk, he showed you something about the square root of 2 is irrational, if you remember. Okay, I teach discrete mathematics, and I'm gonna show you a method. I think you don't, I don't know. I have not seen it in any book or anybody talk about it. How you show something irrational. I want to start with, but this method does not work always. Because, if you want to look at this question, like to show square root of 17 is irrational, usually we use the same method, n over m, where the GCD is 1, and you end up with a contradiction. But I'm going to show you something that maybe, like, let's see 11. I want to show that this is irrational. Look at this method. Okay, so you deny that this is irrational. So it has to be rational. So it has to be written as n over m. Okay? And it's not big deal. You can show that n and m, both of them, they have to be odd. Okay, you can by squaring that, and you end up n square over m square equals 17. That means n and m, both of them has to be odd. To make it brief, this is like 2k1 plus 1 over 2k2 plus 1. This is how you write an odd number. Okay. Let's square both sides. There is no, you don't have to ask for GCD to be 1. Now let's square both sides. We have 11 equal 4k1 squared plus 4k1 plus 1 over 4k2 squared or k2 plus 1. Okay? All right. Now, just high school math. What this means, 11 times 4k1 squared plus 11 times 4 k1 plus 11 equal, maybe k2 here, k2 equal to what? 4 k1 squared plus 4 k1 plus 1. Okay, can I move the 1 to this side? So what you end up with? 11 or K2 squared plus 11 times 4 K2 plus 10 equal 4 K1 squared plus 4 K1. You see the contradiction now. Divide by 4. If you divide by 4, this is not integer. If you divide by 4, this is integer. This is not integer. You're done. A contradiction. So I'm not using any of the GCD. This method will work as long as the number you select here, this number -1 is not divisible by 4. That's a trick. Because you see, when you divide by 4, you have an integer plus a fraction. So this is one way, a method to show that these, maybe square root of 17 will not work, this method. Because, you know, okay, I'm gonna show you something in that thing, another trick, square root of 5. You're gonna tell me 5 minus 1 is 4, so maybe it will not work, but it will work. You're gonna see another trick. So what this will be, again, 2K1 over 2K2 plus 1. And you do the same trick. So 5 will be 4K1 squared plus 4K1 plus 1 over 4K2 squared plus 4K2 plus 1. Okay, so what we end up with? This is like you can teach that without to anybody. I think high school will, I mean, maybe, you know, you don't have to worry about prime factorization. But as I told you, this method you have to, maybe it work in general, I don't know. 5 or K2 squared 5 or K2 plus 5. Or let me just summarize, I mean, you know what they're gonna do. 4 equal 4K1 squared plus 4K1. So I remove the 1. I don't have to. I skip one step. Because here you have plus 1 and then you move it. Okay, let's divide by 4. Both sides. What you end up with? 5K2 squared plus 5K2 plus 1 equal K1 squared plus K1, dividing both sides by 4. Where is the contradiction?
The right-hand side is even.
This is even. What about this one? What is this number? It's always odd. This is always odd. This is even. A contradiction again. Okay, so I thought I'd share with you this trick for how a grant reminded me with this. So I thought I'd share it with you. Okay. How many of you know about the 3n plus 1 problem? Okay, but how do you know it? Maybe I mean, I'm gonna give you another version of this problem, which is not big deal. Maybe it's the same. But I see that some of you don't know about 3n plus 1. The way I think of the 3n plus 1 problem. What does it say? start with a number, let's say n, positive integer, and you can assume bigger than 1, you know. So it can be written as 2 to the k1 times d, where k1 bigger or equal 0, d is r. We can always do that. No big deal. Now, let me define, let's call this d1. Let's take this number, let's call it n1 equal to d1. Sorry, is it 3d plus 3? Right? 3d 1 plus 1. Okay, can be written as what? Let's call it n2 here. Will be 2 k2 d2, where k2 bigger or equal 0, d2 is r, and of course bigger or equal 1. Okay, what do you think n3 will be? Three d2 plus 1. In fact, the way you learn it, I'm hiding it here in the algorithm. Because as long as it's even, you divide by 2. And then when you get an odd, you multiply with the 3 and you add 1, right? So I'm hiding things. Okay, so what this will be? 2 k3 d3 k3 bigger or equal 0, d3 is r, bigger or equal 1. What is the conjecture? The conjecture we learned that when the way you know it, somehow we're gonna reach 1. In this, if you keep doing, at some point, you're gonna reach nm equal to some m, where m bigger or equal 0. If you keep doing this, at the end, you should end up here. This is another version of the 3D plus 1 problem. You only need to work with the R. And of course, this is exactly what we learned. Because when you reach here, if you keep dividing by 2, you're gonna get 1. Okay, so this is another version for the 3n plus 1. I thought I shared it with you. Yeah, another way to look at it. It's like, you know, a sequence of things, and somehow you should end up with 2 to some power 4. And this is amazing. I mean, to my knowledge, there are some people claim solving the problem, but to my best knowledge, it's not. Do you have any?
I think a lot of people claim.
Yeah. Yeah. Okay. So this is another thing I like to share with you in this informal chat. Okay.
Isn't that problem isn't that the problem that Erdos said that mathematics isn't advanced enough to solve that problem yet?
I don't know.
Someone said that.
Somebody, I don't know who said it. Now here's the thing, the point. There are things in number theory, you can explain it to somebody maybe in high school or less. But I mean, I can mention one problem all of you familiar with. Every even number bigger or equal 4 is a sum of 2 prime. You think, oh, it should be done a long time ago. I mean, I can explain it to somebody, 8 or 9 years old, maybe. But imagine we don't have a solution. And here is, things about computer or whatever fancy machine you use, it supports the conjecture. But in mathematics, we don't accept this as a proof. Okay. Another one I want to share with you about prime numbers. Like choose a number. Huh? I want to choose 200. Even bigger. Let's see, 200. Let's see, whatever the number, 200,000. Put a number there. Look what the results say. There is a number you can start from. All the consecutive 200,000 number, none of them is a prime. Imagine that. And at the same time, what we know, we have infinitely many primes. So you see the gap between prime numbers. Okay, and what is really amazing, you said, how are you going to prove that? I promise there will be no proof. But this is like one line of proof. One line to prove this result. And the proof of that is, remember that you need what? The next 200,000. In fact, you can improve it. You can make improvement on the statement when I show you the trick. You just play with the trick I'm gonna do. You can show that the next 200,000 odd numbers, none of them is prime. Okay, here is how you do it. Let's start with 200, if you remember the trick. That's a number. Okay. Or maybe you want to start with, and then maybe I should start with what? How we're gonna make it work? I forgot. What has to do with factorial? And the next one, maybe this number has to be improved. 200,000 factorial plus 2. How are we gonna deal with the plus 1 here? Maybe
200,001.
Yeah. 2,000. Thank you. That will take care of it. Factorial. Then, okay, how do you show this is not prime? Well, 2 is a factor. What the next one? Right? You get it? And keep going. I mean, this is a huge number, but it's a number. All these, because now this number, 3 is a factor. This number 2 is a factor. Well, this one is not a prime. So you see, you laugh. At the beginning, when I saw this, I said, how you prove this? And here is something nice about mathematics. Maybe some people disagree with me. They always look for hard proof. Now you know it is trivial because you know it. But don't tell me it's trivial for somebody thought of that. It takes time I mean, we are in the business. I think you understand what I'm talking about. As soon as you thought about what to write, what's left become details. But don't tell me that is trivial observation. No, it's not a trivial. That you start from here. When you know it, it's trivial. Okay, anyway, so you know how to improve it if you want. You can do even odd. Maybe you make this number bigger, and you start adding 3, 5. And this has nothing to do with this number. You can choose any number, like a billion. Imagine a billion, or maybe there are many numbers bigger than a billion. There is a number you can start from. All the consecutive, none of them is a prime. And at the same time, we have infinitely many prime. If this is not magic, I don't know what magic is. Okay. There is another something amazing, and the proof also, I will not prove it, I'll let you think about it, but the proof 3, 4 lines. Give me, like, randomly, numbers, 5, distinct, positive numbers, distinct.
61.
65.
47.
47. 751. 51. 1, 2, 3. We still have 2 more.
16. 16.
68.
Sorry.
Okay.
1.
1. Okay. So these are 5 numbers selected randomly. There should be some numbers out of these. If you add them, 5 will be a factor of the sum. So exist some numbers from the list say number 1, number 2, maybe number 1, and k, where is k less or equal 5. You can choose all of them, or maybe just one of them, maybe 2 of them, such that 5 is a factor of S1 and 1. And this has nothing to do with the number 5. Give me number 100. So you have to select how many? 100 distinct numbers. Then there should be some numbers in the list. When you add them and you divide over 5, you get an integer. That means 5. Do you see anybody see a proof for this? I think you do, I'm very sure. But don't you think this is amazing? Or I'm exaggerating? I mean, this is true for choose any number. Like I want to choose 1,000,000. If you select randomly 1,000,000 number, then you know there should be some numbers from the list you selected. When you divide them by 1,000,000, you should get an integer. Okay, so this is kind of amazing to me. I'm going to show you some more, and I leave for me the best for last that I love to watch. I'm going to show you something about these 2 numbers, why they are unique. Do you know this? How many of you? So I skipped that.
No, we shouldn't do
We know what, it's 37.
I mean, what do you see? The R prime, right? What do you see the relationship between these two prime? They are the mirror of each other, right? Okay, if you start counting the prime numbers starting from 2, 2 is number 1, 3, 5. Okay, this will be number 12 in the list. So the 12th prime number is what? 37. What do you think this number in the list? 21. The mirror. The mirror, these are, to my knowledge, the only 2 prime satisfy this property. The mirror of each other. And this is number 12 in the list. The mirror of 12, 21. 73 is the mirror of 37. I mean, maybe coincidence this is, but it's amazing to me. I mean, this is not. And why only these 2? Yeah.
As if I looked at different number bases, like
Sorry?
looking at n base 8, base 5.
No, I mean, talk about the normal one. I don't know about. You can work on that. Okay, maybe this one you know. What is magic about this number? 6174. Anybody has a calculator? If you don't mind, if you have a calculator. Okay, how many digits is this number? 1, 2, 3, 4. Give me any number randomly with 4 digits. Any random.
1,101.
Just digit by digit, I'm slow, from left to right.
1,
1.
1.
all ones.
Yeah, all ones.
Oh, just a minute. At least, I think, let me remember. At least 2 distinct or 1 distinct should be. Let me think again. At least 2 should be distinct. So 1, 1, 2, 2. Oh, at least 2. So 2, 3. How is that? Well, yeah. I need to add, remember exactly. But don't tell me 1, 1. There is a restriction on that. I think not all distinct. I think like if you give me 4, then there should be 3 distinct. Like this one, 3 distinct digits. 1 and 2 and 3 in it. 3 distinct. Okay, let's write this number in descending order. Like the highest digit to the descending. 3, 2, 1, 1. Write it in ascending. It will be 2 minus 1, 1, 2, 3. Can you tell me what is the number? What is it?
2098.
2088. Right?
95.
Is it? Okay. Now let's repeat. Let's write this number ascending minus descending. What will be? 8, 8, 2, 0 minus 0, 2, 8, 8. What you end up with?
8,532.
8,000.
530.
2? Okay, let's repeat. Again.
Was already in.
Yeah, so 8, 5, 3, 2, minus 2, 3, 5, 8. What this number?
6,174.
6174. Now, try this. Minus itself, what you're gonna get? You stop here. Because after that, if you continue, you're not gonna get anything in you. If because look, you're gonna do 7, 6, 4, 1, minus 1, 4, 6, 7. And that will give you this, isn't it? So if you choose any number, 4 digit, 3 distinct digit in it, and you write the number in ascending minus descending, and you keep doing that, at some point, you're gonna reach always 6147. Always. You can try that and don't one, that's a good one. 1, 1, 1, 1. Minus 1, 1, 1, 1. Yeah. I mean, I'm very sure you can explain it. And I mean, I'm very sure this one, if you write it in like digit, yeah. But this number is amazing. Turns out. Okay. All right. What else I remember? Thanks. How many of you heard of Mersenne numbers? Okay, Mersenne numbers, they are prime numbers. They look like 2n minus 1 is prime. Any number in this form, we call it Mersenne prime. Like if you take 2 squared minus 1, 3. What about 2 to the cube minus 1? 5. 2 to the 5. 2 to the 7. Is that one? Sorry. I am in a lecture. I talk later. Okay. Anyway, to make the story, how many minutes left for me, Jim?
20.
Oh, okay. It's known if this is a prime, n must be prime. 2 to the n minus 1 is a prime. If 2 to the n minus 1 is a prime, then n is a prime. It is not if and only if. Okay, the question till now, we don't know the answer. How many Mersenne prime are there? So a Mersenne prime, it has to be 2 prime minus 1, and that should be prime. 3, I think, what would it break down? When you 17 will 23 maybe break down. 2 to the 13, 23 minus 1 is not prime. I remember. Anyway, to make it short, till this minute, to my best knowledge, with all the fancy machine we have, we only know 51 Mersenne prime. Only 51. And the last one was discovered 5 years ago by some engineer playing with machine and things, you know. And I think the number was here 7 digits. 7 digits prime number. -1, it turns out to be prime. I cannot remember what's the prime here, but the prime number here is gonna have 7 digits in it. And that is number 51 on the list of Mersenne prime. Okay, so till now, even with the fancy machine we have, we only know 51 Mersenne prime numbers. And no, we don't know, we cannot prove there should be a finite number of them or infinitely many of them. And why we get interested in Mersenne prime? Mersenne prime is related to another problem in number theory, perfect numbers. Because if you solve one of them, you solve the other one. Perfect numbers, like if you take 6, what are the proper divisor? Forget 6. What are the proper divisor of 6? 1 or proper factor. If you add them, what you get? 6. So the number 6, we call it perfect. If you take the proper divisor and you add them, you come up with the same number. And like if you take 8, what are the proper divisor? 1, 2, 4. If you add them, you get 7. So 8 is not perfect number. What about if you take 28? What are the proper divisor of 28? 1, 2, 7, 4, 7, 14. Add them. It should be 21. If you add 1 plus 2, 3, 7, 14, plus 14, 28. So 28 is perfect number. Okay? Now, here is the outcome of what? The connection. Remember, if you have a Mersenne prime, then this prime has to look like 2 to the prime minus 1. Right? So, and here we're looking for the even perfect numbers. Even. I'm not sure if somebody spoke about the odd, I don't know. But I'm talking about the even perfect numbers. Okay. So if n is even and perfect, if and only if we have a result, n can be written as 2p minus 1, 2 to the p minus 1, p is prime, and 2 is prime. So what does this mean when p is a prime? 2 to the p minus 1 is a prime. This means this here has to be what? Mersenne. So if we know there are infinitely many Mersenne, then we know there are infinitely many perfect. And if we know there are infinitely many perfect, we know there are infinitely many Mersenne prime. Okay? Like the numbers I gave you, 28 and 6, like you did the prime here, 2. 2, 2, 4, minus 1, 3. 2 to the 1, 2 times 3, 6. Like 28. Why 28? 2 to the 1. 3 minus 1 is 7. 2 squared, 4. 4 times 7, 28. As long as this here is a prime and P is a prime, then you're gonna get, and this is if and only if. If and only if. Okay. All right. I find this is amazing about Mersenne and these things. And another amazing thing I came across about numbers. No, I think I will end up my talk with one more result. In calculus, how do you show that this is diverge? Calculus 1 or 2. What's the technique usually we use in the classroom?
Well, you can do a partial sum if you're very careful about skipping over certain things, but
Or you not have integral,
the interval test is usually.
right?
Yeah.
Is that what we do?
Group up the elements.
Huh?
Group up the elements in the.
Into powers of two.
Into
Yeah.
powers of
Yeah.
2, right? And what about if I show you something does not need any calculus, only high school math? Okay, I end up my talk with this. So let's assume it converge. Okay, so what that mean? 1 plus half plus 1/3 plus 1/4. Keep going. Converge, right? So it converges to a number. Let's call it what? S. Okay, let's divide by 2. So what we have? So divide by 2. We have half plus 1/4 plus 1/6 plus 1/8. What do you observe about the denominator? The even plus 1/10. What that would equal to? Right? So what is missing from this sum? The fraction where the denominator is what? It's R. Okay, so that means if this add up to S/2, the whole sum is what? S. What do you think the odd will add up to? S/2, right? Because the whole thing add up to S before I divide by 2. The even add up to S/2. So that means 1 plus 1/3 plus 1/5, 1/7, 1/9. Keep with the odd. This has to be S/2. You agree? Okay. By staring, what do we observe about 1? Bigger than half. 1/3. 1/5. 1/7. 1/9. So what do you conclude about the sum of the odd should be? Strictly bigger than what?
Itself.
S/2, which is a contradiction. So this is how you show it. 1 is bigger than 1, strictly bigger. 1/3 bigger than 1/4. 1/5 is bigger than 1/7. Keep going. So we end up 1 plus 1/3 plus 1/5 plus 1/7. This is bigger than S/2 contradiction. That's it. You don't need calculus, you don't need integral. But of course, this is one you cannot, like, I'm not sure if you can modify this into other. This is one of my favorite. How to show, this thing diverge. Okay, I thank you very much. I hope I entertain you. And thank you. Can I have a picture with you guys?
Oh,
I love pictures. This is like, I travel in order to take pictures. If you don't mind. Okay. Can you take it with my mobile?
absolutely. Yeah. So you want to go back
There's
there?
a DNA.
Huh? I'm gonna
Oh, are there any
Oh.
questions out there?
So I can take
See you
two.
later, Alex.
Yeah.